as Lee mentioned, my name is Johanna Mathieu, and I'm a postdoc at the Power Systems Lab at the Swiss Federal Institute of Technology, which is in Zurich. And ETH is the German acronym you can see up there, and I'm not going to try to say it in German, although I'm sure some of you could. So today I'm going to tell you about harnessing distributed flexible resources for sustainable electric energy systems. Whoops. Okay. So my research is motivated by the changing nature of the electric energy system. So in the past, the electric energy system has been characterized by large thermal power plants and few renewables, except for hydropower, providing most of the energy in the system. And in the past, also, the system has had a demand side, so consumption by people that is largely uncontrollable. And what I mean by that is you consume energy when you want to consume energy. The system doesn't care so much when you consume energy. It just has to provide it to you. But now, because of a variety of environmental goals, because of renewable portfolio standards, carbon taxes, and different discussions about different carbon mechanisms, energy security goals, so making sure that we have the energy we need, and demand growth, the system's changing quite a bit. So in the future, we expect the system to look quite different and have lots of renewable energy and possibly electrification of different things like electric vehicles. And the reason why people are talking a lot about electrification is because then we can provide their power from renewable energy. And the system is also changing in a way that people mention the smart grid. So the smart grid is not a very well-defined term, but the way I think about it is a new overlay of sensing, communications, and control that really help us understand what's happening in the system in real time and control it to perform better. And so because of the smart grid, instead of demand being largely uncontrollable by the central system, demand can now be partially controllable, which means that we can control when energy is consumed in some cases, and that can really help out the system. And so this talk is going to sort of focus on that area, and I'll dive into that a lot deeper in the subsequent slides. So to talk about the challenges of this new power system, I'm going to first talk about the challenges associated with integrating high penetrations of renewable resources. So a main issue with these resources is that they're intermittent and uncertain. And so over here, you can see 1 day of solar production from a large solar power plant in Arizona, and every time a cloud goes by, there's no production. So you get this very up and down wiggly signal. And that doesn't look at all like a controllable thermal power plant. Usually we can control power plants very well to output what we want, but these produce when they produce, and we don't have very much control over them. And on the bottom, you can see wind power over the course of a month, and then there's large chunks of time where there's no wind at all in the system. And this is for the entire Oregon Balancing Authority here. So it's actually a lot of wind that's gone all of a sudden. So we need new things in the system to help compensate for these issues. One primary thing we need is energy storage, but more generally, we need more services in the power system to make sure that supply and demand are balanced at all times. And there's high-frequency services called things like load following and regulation that provide minute-to-minute or second-to-second balancing of power systems. These new renewables can also have inadvertent environmental effects. And what I mean by that is if you have to provide backup capacity because you have a solar power plant that looks like this, and then you need a generator like a natural gas power plant sort of providing the opposite, so the total signal is flat, the natural gas power plant's ramping up and down. And when it does ramp up and down, it's not very efficient, and it can also be emitting high levels of pollutants like NOx and SOx. And so if you have renewables in the system, you can actually have other types of environmental issues associated with them. So we really need to consider system solutions, systems that look at the total effect of these new systems on the power system. And of course, we need cost-effective solutions. So we need solutions that don't cost us too much money. We don't want to necessarily build enormous lithium-ion batteries that exist all over in the system because that would be very expensive. So how can we find solutions that actually don't cost as much as that? So in sum, the power system is really operating much closer to its limits. And there's different options people propose to deal with this issue. So borrowing language here from Amory Levin's famous paper from the Foreign Affairs Journal in 1976, where he was looking at different energy trends and patterns in the US and proposing a soft path versus a hard path. In my work, I also sort of formulated a soft path that I propose. So the hard path would be to build out the infrastructure, to solve the problem by building more infrastructure, and get a lot of centralized energy storage, so large batteries, large hydrothermal power plants that can pump water uphill and down, and sort of just build everything out. And the soft path is to try to do better with what we've already got in the system. So do energy efficiency, operate the system better using algorithms and control, and use distributed flexible resources to do the things that the power plants that we're trying to get rid of used to do, because we need to provide the services that they aren't going to be providing anymore. So in this talk, I'm going to focus on this last issue. My research addresses all three of these issues here, and I'm going to talk a little bit about operating the power system better, the second issue, at the very end. So as an outline, I'm first going to tell you a little bit about distributed flexible resources. I've used this term several times and haven't formally defined it yet, but I'll do that next. And then I'm going to show you a case study where I look at modeling and controlling aggregations of small electric loads to provide services to the grid. And then I'll show you these research snapshots. So first, distributed flexible resources. So what do I mean by this? So distributed flexible resources, the way I think about them are any resources that already exist in the system or might exist in the near term that can provide some amount of flexibility and help us really balance the grid and use resources effectively. So a primary area for distributed flexible resources is in the demand side. And what I mean by that is electric loads. So commercial buildings, or buildings like this one, can actually have some amount of flexibility. And residential electric loads, your refrigerator, your air conditioner, your toaster, we can sort of use these loads and change when and how much energy they consume, and that can provide flexibility to the system as well. And industrial facilities, the prime example there is aluminum smelting plants. These aluminum plants can change exactly when they're using lots of energy or little energy, and that can help out the grid. Energy storage also can help out the grid. So in a lot of areas, there's these large pumped hydro plants. And what I mean by that is hydro plants where you can pump the water back uphill, not just downhill. So that's a form of energy storage. It's very common in Switzerland, where I am now, and there's also some in California. Batteries, flywheels, supercapacitors, all the sort of new energy storage technologies people are talking about, they can really help us provide flexibility in the system. And distributed generation itself, like PV panels, wind, and so forth, we can build flexibility into these systems so that they're not just operating according to ambient conditions. The wind farm isn't just outputting whatever it needs to output based on the input of the wind, but you build in some controllability so you can change the production and reduce the production or increase the production. So in this talk, I'm going to primarily focus on just this demand side issue. And so first, I need to define terms a little. So first, demand response. So my talk is going to focus a lot on this issue of demand response. So this is using the demand side to help out the power grid. So the definition here is changing when you consume energy or how much you consume. And so usually you get sent a signal from some entity, I'm calling it a load manager here. And a load manager could be your utility. So the utility sends you a signal and says, reduce your energy consumption or change it so it's outside of some window when the power system is stressed. And it's easiest to understand this by looking at examples. So here's an example of a demand response program in California. And this is a program that I studied a lot during my PhD. So this demand response program is for peak load shedding. And what I mean by that is when the system in California is really reaching its peak, which means that there's not much capacity left in the system because everyone's using power. It's a hot summer day. And we just don't have any more power plants to come online. Power becomes very, very expensive, and the system starts nearing its thermal limits and might collapse. You might have a power outage. But in this demand response program, you can send signals to buildings and have them reduce their consumption at these key periods of time, and that can save the system. So these programs are called a certain number of times every summer. And here is an example of a bunch of buildings that participated in the program. So I have an office building, a furniture store, which is an IKEA. And if you notice, the IKEA is 1 megawatt peaking IKEA, which is a very large amount of energy that's being used by this building, and a bakery. And what I'm showing you is this thin line is how much energy they consumed over the course of one day. And the thick line is how much they would have consumed if they hadn't been sent a signal by the utility to reduce their consumption. So subtracting the two, we can see how much energy they're saving between the hours of 12 and 6 p.m. And they're incentivized to reduce their consumption during these hours because during this period here, between 12 and 3, their electricity price goes up by 3 times the normal price. And then here by 5 times the normal price. So they're really encouraged to shift energy use outside of this period. So the IKEA, for instance, changes the set points in the thermostats, turns off some of the lights, and tells its customers that it's helping out the grid. And so that's how these programs have traditionally worked in the system. And you can see they perform in different ways. There's sort of problems with some of the responses. Sometimes they bounce back up afterward. Sometimes they don't do anything during the period. They wait till the one that really matters. But this is an example of sort of a traditional kind of demand response program. So in traditional programs, the utilities have focused on encouraging large loads to participate because if you have a large building or a large industrial facility, you can get more of an energy reduction from one building. And they have focused on peak load shedding on the hottest or coldest days because that's when the system is reaching its capacity. And the demand response signals are usually open loop. And so what I mean by that is usually somebody's telling them that tomorrow is going to be a demand response day, you should do something. But then in real time, there's no feedback. And in some cases, you actually have somebody calling you up on the phone and saying, tomorrow you have to do something. So it's not even an automated system. And so these programs, while they have a positive net effect and are used widely in the US, they're perceived as a little bit unreliable because you can't usually guess very well how much effect you're going to get, how much reduction you're going to get in energy. And so using these concepts, we can start to think about new kinds of demand response. So now we have systems where we have the ability to decrease energy consumption and potentially shift it around. And so we're now starting to focus on using smaller and smaller loads to do the same thing. And the benefit of smaller loads is that they're very simple systems and usually have simple controllers. Like your refrigerator is a much simpler system than the HVAC system, the heating, ventilation, and cooling system in this building. So if you want to make it do something, you probably can get a more reliable response from it. And also these smaller systems are spatially distributed. So if you have a local problem, you can solve that. And these new demand response programs are focused on shedding and shifting any time, any day. And that's to deal with issues like renewables integration, because you have problems with renewables at any time, not just on these peak days. And we're moving more and more towards closed-loop demand response, so using feedback control. And hopefully these systems will be more reliable in the future, but that's the subject of our research. So as going back to the outline, the next part of the talk, I'm going to talk about this case study to look at modeling and control aggregations of small electric loads for fast timescale energy balancing. And I'll describe the problem in detail in the next slides. So the goal here is to use aggregations of small loads to provide services to the power system. So if I look at a bunch of uncontrolled loads, so here maybe I have a bunch of refrigerators together. They're consuming this much over time. So uncontrolled means I'm not controlling them. They're doing their own control. And then I send them a signal from the system. And I say, if you can follow the signal, you'd really help out the grid. Because here we don't have very much wind power, and here we have too much. So can you change a little what you're consuming? And then my system, my controlled loads, try to follow that signal the best they can. And the important thing to note is that the integral under this red line and the integral under the blue line are the same in this case. So all I'm doing is shifting energy consumption. I'm not decreasing it, like in the example I showed you before. So as long as the loads can sort of store a little bit of energy, maybe they don't even see a real effect in the system because I'm just changing when they're consuming. I'm not actually decreasing their consumption. And so the sort of loads that I'm really interested in for this project are thermostatically controlled loads. So you probably have many of these in your household. It's any load with a thermostat. So refrigerators, water heaters, and so forth. And the great thing about these loads is that they operate within a deadband. And so I'm going to describe that in a second. But the cool thing about this deadband, the fact that they operate in an on-off mode and follow a duty cycle, is that we can think of them as storing thermal energy in this temperature deadband. And we can think of them a little bit like a thermal battery, like an analogy to a chemical battery. So what does a deadband look like? So this is a deadband for a thermostatically controlled load. And so this is a temperature axis, and here's a set point that I have. So if I have a thermostat in my house, I'd set the set point here, but we don't track the set point precisely because then the device would be switching on and off very fast. It can only be on or off. These devices usually can't modulate their power continuously. They're only on or off. So instead of being here all the time, they modulate their power by going plus or minus some value, so delta over 2 in this case. And so if I'm not controlling them, if they're just doing their own thing, it looks like this. So they start at some point in this circle. And in this case, I have a cooling load, so I have an air conditioner or a refrigerator. And that drifts up until it hits the top of the deadband, and then it flips on. And then I power it down, and it flips off. So that's just how a duty cycle load works. But the cool thing about these loads is as long as I keep them within this deadband, the customer doesn't care. The customer only cares, so the person who owns the device only cares as long as the temperature is between these two bounds. So to extract flexibility from these systems, I can imagine having a system where, again, I'm drifting this way, but then I get a big gust of wind in my system, so I flip it on. And then it starts powering down this way, and then the wind goes away, so I flip it off. So I have flexibility in the system because I can change when I go up and down. And you can imagine then, for just one, it doesn't look very nice. All I get is things that look very discrete like this. But if you aggregate thousands of them together, you can actually get a nice continuous response and follow a signal. So how would we control these loads? So my goal really is high-resolution control, following signals very closely, but non-disruptive. And when I say non-disruptive, I mean I always want them to be in their deadband because I don't want the customer to notice what I'm doing. And so I also want minimal sensing and communication infrastructure, because if I'm interacting with 10,000 different electric loads, I don't want to put a lot of infrastructure on each load, a lot of sensing and communication, because it just would cost too much to make this feasible. So here what I'm showing you is physical layers of the power system. I have a load manager, which might be a utility company, distribution substations, and a bunch of loads at a local level. And so what I could do is send a signal to all the different loads and tell them what I want them to do, a different signal to each of them. But it would be much cheaper if I just broadcast one control to everybody and then they can all respond in a certain way. Maybe they don't respond the same way, but they see the same signal. So this is sort of what I'm aiming for, because this solution is cheaper to just broadcast control instead of addressing them directly. And then an important question is, what information do I need back from them to control them? So I need to know where they are in that deadband I showed you so that I make sure that I'm not disrupting the consumer. So ideally, I would have perfect information about all of them back to me so I can make a really great control decision. But in a more realistic case, when I'm trying to minimize infrastructure, I might only be able to know enough about them to build a great model, but then in real time estimate their state, so where they are in their deadband, from this semi-global level. And then sort of in a worst case, maybe I don't even know anything about them to start. So what is the optimal here? And so the real question is, which case is sort of the most appropriate? In which case can I solve this problem well enough to have these loads participate in markets? So to solve this problem, I need a number of models. So I'm going to introduce a couple of different models and show their pros and cons. So this first model is an individual TCL model. So this model's an individual load, and I'm calling it the plant because I'm using this as my real system. So in this case here, I don't have a real system to play with, although that's the next step, implementing this on a real system. But this is sort of my benchmark. It's a high-fidelity model of what the loads actually can do. So I can model each load with a stochastic hybrid difference equation. And it has two states. So the first state is temperature, and the second state is the on-off state. So all it does is really just describe the motion of one load around its deadband like this. And then it's a function of a bunch of thermal parameters. And this model is in the literature. And so if I want to build a population model of thousands of these, I could stack all of these together, and then I would have a model of my system. But the problem with a model like that is it doesn't lend itself to control or state estimation very easily. So I need to come up with a way to be able to use controls and state estimation tools to control the system of a bunch of different loads stacked together. So what I did was develop this other model, Model 2, which I'm calling a state bin transition model. And this model is the aggregate system performance. So it lets us understand what the aggregate system is capable of doing. And the great thing about this model is it does lend itself to control. So I can use existing control and state estimation techniques. So I'm going to walk you through how it works and give you some intuition for it. So if you first take the deadband, so this is pretty much the same deadband I showed you before, but I'm going to normalize it so the temperature space is normalized right here so that I can put all of the different TCLs on the same deadband. And then I divide it into temperature intervals and then divide each interval into bins. So I have n bin number of bins. And then I can use a Markov transition matrix to describe the motion of the loads from bin to bin. So I can say if I have 10 loads in bin 1, I can say the probability of moving to bin 2, bin 3, and so forth is something that I can determine through system identification. And then if I want to force the system to consume more or less power, what I can do is turn some of them off, depending on which bin they're in. So in this case, if I want to go less power, so I turn these guys off, and I say maybe switch off with a certain probability, and then they switch off and come down here. Or switch on. And so that gives me control over the system. And the important thing to note about this system is I'm using one model to describe the motion of all the loads in the system. So the number of states in this model is just the number of bins I have in my problem. It doesn't scale with the number of loads. And the great thing about this model is I can write it like this, which is a linear time invariant system. And the way the system works is that the x vector just keeps track of the fraction of TCLs in each bin. The A matrix is basically that Markov transition matrix. So it tells me how the system moves autonomously without my control actions. And U is my input vector. So that's the thing that allows me to switch them up and down, like I showed you in the last slide. And the problem with U is it's in the same units of X. And X was the fraction of TCLs in each bin. So this is an absolute fraction of TCLs. So if I send U to the loads and I say, switch 30% of the TCLs in the system, a TCL won't know if I need to switch or not because I don't know what my neighbors are doing. So instead what I do is convert it into a relative fraction. And I say, if you're in bin 2, switch with a probability of 40%. And then I can make an individual decision because I can say which bin am I in. If I'm in bin 2, then I roll a die and see if I should switch or not. And so this allows every decision to be made individually and minimizes the communication between the loads. But the problem with this, to get this switch probability, is I need to take my u and divide by x to come up with a percentage, which is my u rel. And that sort of nonlinearizes the problem a little bit. And y is my system output, which depends on what I measure. So if I measure the aggregate power of the system, that's y. If I also measure the states, I can get that information, and that can be wrapped into y. And omega and nu are the process and measurement noise in my model. So I carry the noise over from the last system. So now looking at a variety of scenarios for communication and infrastructure. So in each case, I'm going to assume that I broadcast control from the central load manager. I send that U vector out to everybody, and everybody says which bin am I in, what probability should I switch at. And I also assume that I can't control TCLs if they go outside their deadband, and that ensures that my control is non-disruptive. And then what I do is I vary the amount of information I have available for all of my control tasks for system identification, state estimation, aggregate power. So now I'm going to show you a couple different scenarios for how the system would work and show you the algorithms that we need to use to get the various pieces together to control the system. So scenario 1 is the reference case. This is the case where I assume I have all information available. And so the most expensive case, I would need a lot of metering and infrastructure. And I would need to communicate with my loads every 2 seconds back and forth. So that's a lot of back and forth, you can imagine. So in this case, I can build my model, do system identification, because I assume I know enough about my loads. So I either know their parameters or I've measured their states over some time, and I've identified that A matrix. And I also assume I know the states and I know the output. So I know everything perfectly. So the easiest case to sort of implement. And then I'm going to start pulling back layers of information. So I have less and less available to me. So in scenario 2, I don't know my state. I don't know X. So in this case, I can build a good model of my system. So I have, with system ID, I still assume I can model my system because at some point I knew the parameters of my system quite well. But now, I don't know my state. I can only measure the output because I tell the loads to tell me if they're on or off. But I don't have them tell me what temperature they're in, what temperature bin they're in. So I don't know where they are in temperature space at all. I just know if they're on or off, which is an easier thing for them to measure. And from that, I can estimate their aggregate power, but I don't know their state. So what I do is I use a Kalman filter to estimate their state. And I can also estimate the aggregate power from a noisy measurement of aggregate power. So if I don't have information from all the loads, maybe only 30% of the loads tell me if they're on or off, I can still use this approach. And scenario 3, now they're not communicating with me in real time at all. So I still have a good model of my system, but now in real time, I'm only getting information at this semi-global level. And this semi-global level, I get an aggregate power estimate, and I get it by coming up with a load forecast at the distribution substation, subtracting what I actually measure at the substation, and then the difference is my control action plus noise, and my control action tells me the aggregate power of the system. So, but it's very noisy because it's all based on a forecast at this level. So based on my forecast error, I get a better or worse answer. And so in this case, again, I need to measure my state, or I need to estimate my state because I don't have a measurement. And the only difference here is I still use a Kalman filter, but now my estimate is I come up with it from the semi-global level instead of the local level. And scenario 4 is the case where I showed you before, where I don't really know my system at all. So in this case, I don't know anything about my system a priori. I don't have a state measurement in real time. And I only get estimates at this level to build my model and to do state estimation. So here, this is a tricky problem because I start without a model. I have a notion of the dynamics of my model, but I don't know my A matrix to start. So here what I do is I can transform my system. So a 2-bin linear system is what I start with. But in this case, I don't know these A variables. And I can transform them into states. And I can rewrite my system as a nonlinear system where my parameters are states, and then use an extended Kalman filter, which is a nonlinear Kalman filter, to estimate the system. And in this case, the output is not just the state and the output estimate, but it's also the estimate of that A matrix. So what does this look like? So that was a bunch of math, and now I'm going to show you some pictures of how things come together. So here, what I'm doing is using 1,000 air conditioners, and I'm trying to track a 5-minute market signal. And this is an actual market signal that is used commonly in a variety of markets around the country. And generators are supposed to follow this signal and every 5 minutes change their dispatch operating point. And I'm just using a very simple controller to control the loads. I look at the desired power consumption in the next time step, the predicted, subtract the 2 and multiply by a gain, and that tells me how many I need to switch. And then I can look at the results here. So scenario 1, this is the perfect case. So this is the best I can do with this approach. I know everything about my system. And I have a blue line that's trying to follow a black line. So my black line is what the dispatch is telling me to do to participate in the 5-minute market. And the blue line is what I can actually do. And it's very close. It's not quite perfect. You might see that there's some up and down wiggles there because there's some noise in my system. Both models are noisy. And also, I have this switch probability thing where I'm sending switch probabilities out, so we might not get exactly the number to switch that we want to. Scenario 2 is the case where they're telling me if they're on-off, but I don't know their temperature. So if all of them tell me if they're on-off, my results look quite similar here. But if only 30% of them tell me if they're on-off, things start to degrade a little, because my estimate's no longer that great. But I can still do some estimation and follow the signal reasonably well. But you can see, as I take away information, things start to go less well. Scenario 3, I'm only getting information about aggregate power at that aggregate level, so at the substations. That's where I get information. So now the loads don't have to communicate with me in real time. And so depending on my forecast, how accurate my forecast is at the aggregate level, with an error of, say, 5% or 10%, I can do better or worse, and it can get even worse if your forecasts are really bad. And then this scenario 4 shows you the case where now I have to learn my model and my state. So in this case, I just start with nothing. And I send some information out. I look and see what happens. I learn a little bit. And then I send more out, and I learn over time. So I'm learning my model and my state. But you can see you start kind of bad because you don't know anything about your system. But eventually, you can sort of start to track it. And in this case, with even more error, maybe you get more zigzags and so forth. And sometimes things can fall apart a little because the model can have drift. So this is what all the cases look like. And an important thing to think about is, well, how does this performance compare to that of a generator? So I'm proposing that these loads are trying to provide the same service that a generator provides. And generators aren't perfect either. Like, a generator can't follow a signal perfectly. And importantly, they tend to lag signals because they're large rotating machines. They can't move very quickly. And they have ramp constraints, meaning they can't move instantaneously from point A to B. They sort of have to slowly go where they go. And what we find with these sorts of systems is that they can actually ramp up and down very quickly. They can go up and down. They do have error associated with them, but it's usually approximately zero mean. And so they don't have this lag effect. So it's still up in the air very much which of these is the most appropriate and which scenario we could actually implement in real life. But it's probably something over here, and we probably don't need to do this in order to compete with existing generators. So there's a bunch of important questions we can ask about model parameters. So I proposed a model with a lot of bins in the system, and what I showed you here was that I was using 40 bins or 2 bins in this case, where 40 bins is really hard to do with an extended Kalman filter. But what if we change the number of bins in the system? So just looking at scenario 3, I'm showing you the RMS power tracking error. So this is the error in terms of following this signal. So the more error, the more noisy I am. This is much less error. And in this case here, I'm saying if I have a 2-bin model versus an 80-bin model, how well can I do? So this is more discretization of the state space. And you can see, as I discretize the state space more, my error decreases because I have a better idea of where the system is, and I have a better idea for what the autonomous system, so the uncontrolled system, would have done. So I know how many to switch much better. And I can also ask the question, well, what if I add more TCLs? Here I'm just looking at 1,000 of them. What if I say I have 10,000 loads I can control? So 10,000 air conditioners instead of 1,000. And if I do this, then I find that the error decreases because I have more systems, so I have better averaging and I get better effects. So having more is much better, of course, but then you have more coordination you need to do. And a really important question is then, so I proposed this sort of fancy scheme with this fancy model and state estimation and Kalman filters and all this stuff. What's the value of this? Could we just do this much more simply? Could we just have a little proportional controller and just do input-output control? Because it's always important to go back to the basics and say, could I do this much better with less? So what I did was look at, if I just have a very simple controller, it just looks at an input, it looks at an output, it adjusts the system. And so I use my proportional controller, control the system the best I can, tuned it as best as I can, and I get these results. So I actually find that having a knowledge of the dynamics here really does reduce the error. So knowing something about the dynamics of the system helps you a lot in this problem. So my key findings for this work were that having models and using the state and parameter estimation techniques really do help us reduce the need for data and infrastructure. And that's really important right now because fast time-scale telemetry, so telemetry that actually allows you to exchange information on timescales of seconds, can be very, very expensive. And so it's really important to reduce the need for that. So if you only need to have one at an aggregate level instead of 1,000 distributed, you can really reduce the cost of this sort of scheme. And then I did a study to say, does this really matter? So I think I talked to somebody about this today, but what's the scale of this sort of thing? If I take every refrigerator in the state of New Hampshire, do I actually get anything meaningful out of this? Is it big enough to really even be worth it? So I didn't look at this for New Hampshire yet, but that's next. But what I did do was look at it for California, which is where I was living when I was looking at this. And I took all of the air conditioners, electric water heaters, refrigerators, and heat pumps in California, and I tried to calculate the energy and power capacity in the thermal battery in the state of California if I could access every one of these loads and use the existing deadband. So I'm not asking the consumers to change anything with their deadbands. They still have the same size deadband. But how much thermal capacity do I have in there? And that's kind of a battery in a system. It's a thermal battery. So I have to characterize it in terms of its power and its energy. And you see that it's quite large, gigawatt scale. So actually, this is a huge potential if we could access it. But of course, the economic potential, what makes sense economically versus technically is going to be much lower. But it's still something that's reasonable to think about. And also an important issue is revenue potential. So if you had a guy who wanted to be that load manager, they're going to say, well, can I make any money off this sort of scheme? Is it really going to pay back, or is the infrastructure going to dwarf all the money I would make? And so I also did an analysis where I looked at a variety of different sources of revenue potential for participating in markets using existing market prices, and said how much money could each load make if they participated in the system. So here I'm showing you results if they participate in a frequency regulation, which is where they follow a signal that changes every 4 seconds. And so if they participate in this, you get different answers based on the type of load, because each load has a different energy and power capacity, so a different amount that they can offer to the system. And so if you have air conditioners, they can make $10 to $80 per year. And why I have such a huge range there is it depends on where your air conditioner is. So in this case, if you live in Berkeley, California, where the temperature is beautiful all year and you never need to turn on your air conditioner, you make about $10 a year in about 2 weeks that you actually turn on your air conditioner, or maybe a little bit more than that. And then if you live in the desert, you start to increase your potential. You also pay more for your air conditioning, but you increase the flexibility you can provide to the system. And then electric water heaters and refrigerators look like this. And so the question is, well, if I can only make this much for each of these loads, can I then use a portion of that money to pay for all the infrastructure costs, and then somebody who's acting as a middleman, will they make a profit? And I think, given these numbers, these revenue potentials may cover the cost if we don't have to have a metering point at each individual load, if they just have to respond to signals, but they don't have to give us information back. So I think that there is potential here. And an important point is these numbers are really maybe not even order of magnitude correct going 10 years into the future, because in the future the markets will change, the prices change, the revenue potential changes, especially as we have more solar and wind power in the system. Actually, the prices will probably be more volatile, and so you'll have higher revenue potential in the future. But this is conjecture at this point. But we can say that at least there's the potential for it to work. Okay, so going back to the outline. Now I'm going to tell you a little bit about one more scheme for how you can make money. I'm sure you aren't concerned about how to make money on this, but it's a really interesting controls problem here of how do you arbitrage electricity prices, and how do you sort of extract some benefit from participating in 5-minute electricity markets. So what is energy arbitrage? So usually if you think about arbitrage, you buy low, sell high, right? But here you always have to buy. You're an electric load, you have to consume energy. It's just a matter of when you consume it. So you want to buy more when the price is low, less when it's high. And you want to use price forecasts, so forecasts into the future, to figure out how to minimize your energy costs over time. So if you imagine the system, you have some kind of system operator, it's sending you prices. You have a load manager who's then controlling loads. So this part of the problem you've seen before. And now I'm saying you have somebody else telling you prices. You don't have them telling you a signal to follow. So now, instead of a tracking control problem, it's an optimal control problem where you need to figure out what trajectory to follow yourself to minimize your costs. And some work has been done in this area, but none of the work has considered these specific TCL models. And these models don't act just like traditional energy storage units. And so that's what's innovative about this. And ideally, we'd use this model too. So the state bin model that I showed you, the state space model, to do this problem and solve it as an optimal control problem. But it turns out that this model has limitations. When I push the system to its constraints, so I push all the TCLs to be off or on for too long, the model starts to break down. And that A matrix, the transition probability matrix, actually doesn't stay constant. It starts to change. And so we can't use that model for this problem, for the optimal control problem. So what I'm going to show you is this model 3. And the really cool thing about this model, is I'm calling it a time-varying thermal battery model, but what it's basically showing you is that everything, all of these sorts of systems can be thought of as batteries, but they're not normal batteries. They have an energy storage component, but you can imagine if you had a battery, like if I was holding a car battery right here, my battery, in this case, is changing in size over time. So it's not static. So it's a little bit of an interesting problem to think about. And if you've ever played with battery models before, you can model the state of charge, so how much energy is in the system, with an equation that looks a little bit like this, but I'm having everything vary as a function of time. So it's a little bit harder to think about. But what I have is the current amount of energy in the battery as a function of the past energy in the battery, and my power withdrawal or injection versus a baseline. So if I have a population of air conditioners over the course of one day, their consumption would look like this if I don't control them. So the temperature increases, the temperature decreases, they consume this much energy. But what I want to do is pick the power consumption to minimize my costs of energy over some time frame. And that power consumption that I can pick is constrained by the size of my battery, by the Pmax and Pmin here. And so I can only flip on a certain number of loads at any time or flip off a certain number. And if I'm over here where none of them wanted to be on anyway, I can't do anything. So my battery is changing, and sometimes I have no flexibility, and sometimes I have a lot. And I also have constraints in terms of my state of charge. So the state of charge tells you the energy content of the battery. The energy content is also changing over time. And so if I look at a feasible trajectory I could follow, so I could follow a trajectory that looks like this, and this trajectory could help me minimize my energy costs over time. But it has to be subject to all of these constraints and this dynamical equation. And the real hard part about this problem is estimating what's the size of my battery and how does that change over time, because that's a function of the real physical system. And so what I do now for this problem with air conditioners is just say, based on the outdoor air temperature, I can estimate how many would be on at any time, and that can help me define my Pmax, Pmin, Smax, Smin. So I just look at what the current temperature is. But that's not a perfect assumption, which I'll talk about in a second. And I can implement the arbitrage problem via a two-step problem. So the first step is kind of the new step. So I solve a receding horizon linear program using this Model 3 to find this optimal trajectory, so something that looks like this, versus a prediction of energy prices into the future. And then step 2, you've already seen. This is the point where I then try to follow that trajectory. And so that's just like the previous problem I showed you. So I need to split it into 2 problems. And so what does this look like? I think seeing a picture would help you understand this more. And so if I look at arbitrage with 1,000 air conditioners, and I use a 1-hour prediction horizon, so I have a 1-hour prediction of prices into the future for these 5-minute prices. And I'm using actual energy prices from markets in California. So the prices look like this in this case. Between 12 and 4 p.m. And then I can use that Model 3 to find an optimal trajectory. So I can see here the prices are increasing, so my power consumption is trying to decrease, and so forth. And so this is what I get optimally from that third model. And then I use my Model 2, so my state bin model, to develop a controller. And then I make the controller control all the TCLs that are modeled with my high fidelity model, my plant, which is Model 1. And what Model 1 does is what I assume the real system would do. And it looks like this. And you can see here, it doesn't follow it that well. It doesn't follow it that well because this Model 3 is very coarse. It doesn't model the system in great detail. And estimating those power and energy capacities isn't very accurate. But the important thing with this problem is it doesn't matter how well I'm actually following the trajectory. It just matters how much energy costs I'm saving. So as long as I'm sort of following the general trend, it's still pretty much okay. So if I want to look at the best case air conditioner energy cost saving, so what I mean by this is I assume in this case, I'm just trying to see if this problem even makes sense. So if I knew prices perfectly into the future, and the prices look like they do today, and that I'm not affecting the prices, how much energy costs could I save in a system? So given real prices for an entire year in Merced, California, 5-minute prices and weather data that corresponds to this location, what I'm showing you here is a histogram. So this is the number of days per year I can save this much money for 1,000 TCLs. You can see most of the year I save almost nothing. The prices just aren't that variable. And if they're not that variable, I can't really arbitrage them very well. But then I do have some days in the year where the prices go crazy. And I can really arbitrage those prices great. And sometimes they even go negative. I get paid to consume power. And in that case, you consume as much as you can because you can store it. And then in the future, you don't consume as much. And so you have all these opportunities here for saving a lot of money. But for the entire year, things don't look that great. If I do arbitrage for a whole year, I can save $13 per year, not very much money. So does this make sense to do? And I think the answer here is that it makes sense to do on these days, and the rest of the days per year, you have this great infrastructure you can use for something else, like providing frequency regulation, like I showed you before. So there's a lot of really interesting opportunities to think about how do you improve the value of these resources, potentially by multitasking them, having them do different things at different times based on which potential they can give best to. So there's a lot of interesting coordination, optimization problems, and then how to actually control them to do the task. So here I started showing you my current and future research ideas in this area, but I think that there's a lot of opportunities for new models, estimators, and controllers. So I showed you that that third model has a lot of inaccuracy because of the way we estimate power and energy capacity. So there's a lot of potential to reduce the error of that model and explicitly model the uncertainty so that we can use stochastic approaches instead of deterministic ones. And then there's also lots of options for better estimators to deal with non-Gaussian noise and different approaches. So right now I'm looking at very centralized control approaches. Each of my loads is making decisions about whether to switch or not itself, but based on a central control action. Could they each individually make their own decisions based on less information from a central control to really minimize communications even further? So there's a lot of interesting work that can go on with agent-based modeling, contract design, decentralized control, and I've started working in this area. There's also a lot of interesting questions about market interactions. If I'm playing in energy markets, if I'm big enough, I'm going to start affecting the prices, which is going to decrease my potential to make money in these markets. So how does that look going forward? Is there actually a revenue stream from this sort of thing? And then a really important issue here is environmental impacts of this sort of work. So if I'm changing the way the grid is being run, I'm changing the dispatch of the system. I'm changing which power plants are going to be actively producing power and providing backup reserves. How does that affect things like greenhouse gas emissions and other types of emissions? If, for instance, I displace a natural gas power plant with my scheme to use energy storage from thermal loads, and then that natural gas power plant goes away, and instead of it producing energy, some coal power plant comes in to produce energy. So there's a lot of really interesting interaction issues here that could be studied in the future. So quickly, I'm going to just go through some research snapshots. And so at the beginning, I just showed you the soft path solutions that I'm most interested in exploring. I've talked a lot about the first one. I'm interested in building energy efficiency, but I don't have that in this talk here. And this last one, operating the power system better, is another thing I'm interested in. And this one doesn't really even require any additional infrastructure. It's just algorithms for how to set up the power system so that it could work better with what we've already have in the system. So 2 snapshots briefly. One is thinking about power systems with uncertain reserves, and then electricity markets. So power systems with uncertain reserves. So generally in the power system, we have this really important problem, which we call the optimal power flow problem. It sounds big, but basically it's just an optimization problem, which says if we need to figure out which generators in a system should, at any instant in time, be producing energy, we need to look at their costs and their constraints, and we need to look at the grid and its constraints, transmission lines, distribution systems, and put all that into a big optimization problem and decide who produces energy when to maximize efficiency of the system, economic efficiency, basically to minimize costs, but also make sure that the system is reliable and secure. So this is what we solve, an optimal power flow problem. And a lot of research is done on this problem, especially if you start looking at issues like you want to make sure that this optimal power flow problem is robust to contingencies, which is the word power engineers use to talk about grid emergencies, like if a power line goes down. So people propose security-constrained power flow problems, so make sure that the grid security is maintained. A lot of people have looked at if we have uncertain wind and solar energy, how do we make sure that this problem is still robust to wind and solar being uncertain? So they propose stochastic optimal power flow problems and problems that endogenously determine reserves. So what I mean by that is reserves are backup capacity. How can we determine how much backup capacity we need by looking at the statistics of the wind and solar power here? So we look at their statistics, and that tells us how much reserve we need in the system. And what I'm really interested in here is, say we have a bunch of cheap but uncertain and energy-constrained reserves. So you can imagine the systems I just talked about. We have a bunch of air conditioners. We have a bunch of electric vehicles, any number of things. And we know that if we can harness them, that they'll be cheaper than other types of reserves. But they're not always available. And usually with backup capacity, we think of them as 100% reliable. But can we actually look at a system where the backup capacity isn't 100% reliable, but it's cheaper, so that we can still involve them in the system, and then probabilistically the system is still safe? Because ultimately, all we can care about is probabilistically what the system state is, because any reserve, any backup is never 100% there. you always have a chance that a power plant could go down. So to look at this problem, I'm just starting to look at this problem in some depth. And if you take the power capacity of 1,000 air conditioners, and I'm plotting that versus temperature. So if you just focus on this black line first, and I say, if it's really cold, this is in degrees C because I work in Switzerland. If you just look over here, it's cold, there's no air conditioners on. Here it's very hot, there's lots of air conditioners, so my power capacity sort of ramps with outdoor air temperature. But if I actually simulate a system and look at how much is actually available, if I look at the dynamics of the underlying system instead of just try to estimate it at the higher level using the models I introduced, I find it looks more like this. So my model's not very good. And that's just what it looks like on average. And if I actually look at the percentiles of where I could be, given it was 30 degrees outside, I could actually be anywhere between this and this range. And there's huge variation here. And not only that, there's this huge variation, but this noise is very non-Gaussian. It looks very strange. And so it's pretty hard to think about how you could solve this problem effectively. So the question is, how do you provide reserves with these aggregations of loads and storage that are very uncertain? And what does this uncertainty look like? First, how can we reduce it? So how can I get that model to match the real better? But how can I reduce the uncertainty or model it in a good way so that I can use tools that take into account Gaussian noise and things like that instead of these really funny noise patterns? And right now what I'm looking at is how we can solve a problem, like an optimal power flow problem, with reliability guarantees where we can still be using these resources that aren't guaranteed to be there when we want them. And an important question, really sort of a policy question, is how cheap would the reserves have to be competitive with the ones that are going to be there 99.9% of the time if my reserves are only 70% reliable? So how cheap would they have to be to make this all work out? So what I'm using for this approach is a scenario approach for stochastic optimization, and this allows us to look at the real uncertainty distribution. So this is sort of the front edge of my work right now, so hopefully I'll have some interesting results to report soon, but I think it's a really interesting problem. And then the last part here, electricity market analysis. So I'm really interested in electricity markets. It sounds like an economics problem. A lot of economists look at electricity markets too, but a lot of controls engineers also are really interested in this problem because markets can be thought of as control loops. And so what I'm showing you here is a control loop. So usually the way the markets work is people consume energy. You look at the output, the total output of the energy consumption, how much we're consuming, and then you run a generator electricity market. And then that market produces prices, which dispatches the generators. And the prices could also be fed back into the demand response loop. And then the loads could see the prices and change their electricity consumption. So it looks like this. Oh, and I forgot to mention, I'm working on this project with two economists, an economist at Caltech and so forth, so that we can really look at how to tackle this from a controls perspective and an economics perspective and sort of put these two together. But the issue with this system here is that you set the electricity prices, but then there's sort of a delay before demand response sees them. And so if you know control systems at all, whenever you have a delay, you could run into stability problems. So if this delay is too big, you have major problems. So the prices you see now were relevant to the system in the past, not now. And so you can use some basic economics tools. And I like these tools a lot because they're very visual. And we can think about them from a controls perspective too. So what I'm showing you here is the current price as a function of the past price. This is an equilibrium price. So usually with economics, you always assume you're at the equilibrium. But in this case, you actually dynamically either converge to the equilibrium or not. And so here's a linear mapping of the supply-demand curve. And here's just where PT equals PT minus 1. And so if you start here, you can curve around. But it all depends on the slope of this linear mapping. So you could also just keep going in circles and never reach your equilibrium. Or you could spiral out of control. So your prices start swinging. And that causes your physical system to start swinging, and you can get huge instabilities in the system. So this is a really interesting area for research. And I'm also looking at now, well, how can you fix this problem? So one idea is, instead of electricity consumption sort of being exogenous to the system like this, I mean, there is some feedback, but a lot of it's exogenous, can the consumers bid into the market too? And then the producers bid into the market, and then it acts more like a normal market. So I'm working on this issue, looking at some game theoretic approaches to understanding how both sides can sort of behave in a more optimal way. So I think I'm just on time here, and these are my conclusions. So I hope I've painted the picture to you that power systems are changing drastically. There's a lot of new challenges associated with these systems, but there's great opportunities too because of this new infrastructure that we have in place, or we will have in place soon. And also, I really think that there's a huge potential for these distributed flexible resources to play a large role. They could really help us minimize new infrastructure by just utilizing existing infrastructure more effectively. So I thought of titling my talk, How Your Air Conditioner Can Help Save the Planet, but decided to be a little bit more formal here. But I really think that it's important to consider how you can also get involved in this. And a last important point is I think that there's just a lot of possibilities for people who work in dynamical systems, control theory, and so forth to really get involved in this field and really help us do more with what we've already got in the system instead of trying to build more infrastructure. So controls, control systems, dynamics, optimization, and so forth play a really large role in this field. And so that's sort of the background that I bring to this. So I just wanted to thank you all for coming. I especially wanted to thank the Thayer School for inviting me today. I have a number of collaborators at a variety of different institutions. I did my PhD at UC Berkeley. LBNL is where I worked a lot. Now I'm at ETH. My funding, and then if you have any questions, you're welcome to contact me. Here's my email address. So thank you very much, and I'll take any questions. Yep, the distribution substation level. Yeah.
How many of those did you assume in your modeling?
In my modeling, so I usually assume that there's 17% of the distribution substation load is TCLs. And I can look at, like, if I aggregate a bunch of distribution substations together, say I assume I have 1,000 loads at each substation, I've looked at cases where I've taken like 10 of them together and looked at the behavior of 10,000 loads, each aggregated at the 1,000 level point. Did that answer your question?
So you're assuming 10 substations?
There could, well, if you have, I'm assuming different things. So I showed you a population of 1,000 loads, I'm assuming one substation. Or if I have 10,000 loads, I'm assuming 10 substations, because it's unrealistic to think you'd have 10,000 loads under one.
So
yeah.
each substation is aggregating 1,000?
Yeah, in this case, yep. Mm-hmm. Mm-hmm.
How much real-world experience have you put into this found from places where this is actually being done? For instance, more than 20 years ago in Illinois, I had a preferred power rate because my air conditioner was under the control of the power company.
Yeah. So there's a lot of examples of power companies getting involved with air conditioner control, but usually what they do is remote switch off. So all they can do is turn you off. They don't do any sensing of of your temperature in your household. They just switch you off for usually a contractual amount of time, whatever you agree on, 20 minutes, an hour, or something, if the system is under stress. And so the benefit of this sort of approach is that I'm not asking you to switch off for some amount of time and having your house get really hot. I'm making sure that whatever you set your set point to, you still see whatever you see. So the real benefit there is that I now know much better what's going on in the system, so I can control you in ways that don't disrupt your life. Yep.
I think in that case, though, with a very large number of air conditioners, they controlled in blocks. So
yeah.
No block was off for enough time so that you noticed it much in your temperature, and the only time when everybody would be off was if there was a system emergency.
Yeah, and so you can sort of consecutively turn people off just to sort of reduce the consumption in the system, and you never would turn people on. But if you want to try to follow these really fast timescale signals that are changing drastically, that's a two-course approach to be able to do that. But yeah, I mean, there has been experience doing these like basic heuristic control approaches in the past. Yeah. Yep.
To what level of detail do you need to be able to sense and control individual units? Because there comes a point where you have to compare the cost of doing that with a much simpler solution, which would be local energy storage, and just switch off the supply temporarily.
To switch off the supply, and that would allow you to decrease the consumption or something. Right. Well, I mean, in the cases I showed, like especially in that case 4, I'm not actually sensing anything locally. I'm just estimating the local effect from an aggregate level. So in that...
You still control the time at which things turn on and off at the individual unit level.
Right, so there's still...
They're
still receiving a command from me, and then they're switching probabilistically if they should or not.
Is what is the infrastructure required to be able to do that? And how much does it cost compared to much simpler solutions of local storage?
So so there's two parts to this. So the infrastructure you would need if you have an existing thermostat is, a lot of the thermostats right now are wireless, so some way to communicate with it. So some little thing that you'd sort of stick next to it that could measure temperature or something and then tell it, I'm in this bin and what do I need to do? So I think that little device would be, once you scale it up, that would be a very, very small cost, like $1. And I don't know that for certain, but I don't think that the infrastructure that you would need to do that would be very, very complicated. But I think the important part is that then you're using the house as the energy storage, which already exists. But if you want to add an energy storage unit and put the energy into that, you need to build something new. And the upfront cost of that is going to be quite expensive. And getting the consumer to do that, or maybe getting the utility to lease something to consumer, is going to be more work than having this little thing that you just attach to the existing wireless thermostat. Or that's my, yeah. Mm-hmm.
How much does feasibility scale with this tolerance level of the thermostat? You could, the epsilon associated with your...
That's a great question.
You could increase that. I'm not saying that it's ideally, that's optimal as it is. If you could enhance that tolerance a little bit more.
Yeah. That's a great question, yeah. Hugely. So I showed you a power and energy capacity. If you increase the deadband size, you don't increase the power capacity. You still have the same amount of air conditioners in the system, but you double, so if you double the deadband size, you double the energy capacity. So you double the amount of energy you can store in the system effectively. It's approximate, but that's about what it is. So you can incentivize consumers more to make their deadbands bigger, so make their flexibility larger. Mm-hmm.
Is there already some existing research on kind of how people feel in terms of comfort levels for different deadband sizes?
Yeah, I know that there is some research in terms of this, and usually deadbands are fairly small. They're like a degree or two, but I think that drifting for 3 degrees isn't a big deal for some people. Celsius, 3 degrees. Yeah.
You could imagine consumers, if you increase the deadband, and realizing, I feel sort of hot, and changing the set point, center of the deadband, and that would compensate, and you'd use more power total.
You'd use more power. Yeah. So with this scheme, you're actually causing them to decrease and increase as much. So decrease as much as they increase. So if they do change their set point, they consume more energy, but we still get the same.
We get the
world
doesn't.
Yeah. Uh-huh.
So how would it be at night when wind energy, which is certainly going to be a much bigger component of the variable energy that's going to be in the system, is occurring mostly at night when there's much less opportunity for operating air conditioning?
For air conditioners, yes. For electric heating, that's not. Oops. And electric heating. So in a lot of places, there is some.
Most people wouldn't want to use electric heater because it would be too expensive.
Well, heat pump heaters are sort of becoming popular in some places. So heat pump heaters, are basically like air conditioners run in reverse, and so they're quite.
You would have to very often dig into the rocks for a heat pump.
A ground source heat pump, yes, but if you just have a heat pump, like an air conditioner heat pump, but running in the opposite, then I think that there's some places in the country where electricity is quite cheap and people are moving towards heat pumps, like in the Pacific Northwest.
With 20% wind energy, which the NREL is talking about, that wind energy would core mostly at night.
Yeah.
So there your opportunities for integrate that huge block of wind energy would be much less than during the day.
So I think there's two things to note. So one thing is nighttime you still have refrigerators, you have water heaters, electric water heaters, you have heat pumps. So you do have some things there. But this sort of scheme would not help integrate the whole part of the wind. So it only does sort of the high frequency variations, and something else would have to do the lower frequency variations. So if there's daily variations in wind patterns, we need some longer term energy storage to solve that problem. This operates best on the seconds to hours timescales.
Good, but then, I think that a lot of what you're talking about could be avoided if you had an hour-to-hour rate schedule. In other words, you have a daily graph for the daily demand, and if you can flatten that demand by means of a rate schedule, so you don't turn on your clothes dryer around 3 or 4 o'clock in the afternoon, because then the cost would be 30, 40 cents a kilowatt hour. So you have a timer on that thing, which turns it on after midnight. Clothes will be just as dry in the morning, and you pay a lot less. And so a lot of people will get the signal real quick if it's something that hits their pocketbook, real time.
Yeah. So
they would call up their local electricians and say, "Gee, put a timer on my dryer."
And I think that plays a really important role. So dynamic electricity prices are really important for making sure people shift energy consumption to the right times of the day, just like you're saying. But for very fast time-scale balancing issues, where you actually need second-to-second resolution of balancing things up and down, you need real-time control strategies, not schedules, I think.
It would only affect the solar, like in California, but then there's not much solar here in New England. Over here, some areas have some wind. That balancing would then be taking place mostly at night.
Right, and so and then there are resources that could help with that at night, I think.
There's a lot to do yet. I just don't see this being implemented within the next few decades.
I mean, yeah, so this is research. It's long term. But there are places, for instance, in Germany that have such high penetrations of solar that they're thinking about.
It's a special case because they're very rich.
Okay. Yeah.
So, a somewhat related question, there's a lot to do yet. Help me understand kind of the time trajectory of this field looking forward. So I understand it's a relatively new issue, and I imagine with a lot of opportunities for great analysis that's going to make a difference because penetration of these intermittent sources is coming on. But fiber, is there going to be a period of that people who are really good at algorithms are going to come up for this for 5 or 10 years, and then there will be diminishing returns going forward? In other words, we'll figure out what there is to figure out on an analytical basis.
Interesting.
And then it'll be just a matter of, the growth curve keeping up in place, but there aren't that many new intellectual questions. Or do you see the intellectual questions going on and even becoming richer with greater opportunities as time progresses?
Going forward in terms of, so once we get to 100% renewables, maybe we've figured everything out.
Long before we get, let's say in the next 10 years, we won't be 100% renewables. I'm an optimist, but I don't think so. But will we be at 90% of the value we can get from algorithm development?
Yeah. So I think that so this is one problem in this space that these sorts of resources could help out with the balancing. But there's a lot of other things that become really interesting as we get to higher and higher levels. So this is relevant as we go from where we are today, like in California, there's 20% renewables up to 100. But then there's other issues that start to arise. For instance, once you start getting rid of all the thermal generators in the system, you have all these large rotating machines that are going away. The system now no longer has inertia. So there's these questions of how do you introduce inertia into the system? Could you use new algorithms and loads and things like wind turbines and solar cells and manufacture inertia in a system? So a lot of the control problems then are kind of similar, but you're trying to solve something else. You're not trying to solve balancing anymore. You're trying to provide this sort of fake inertia into the system. So there's a lot of interesting things that come along in the future once you get more and more and more. And I do think that the field, has a lot of interesting questions coming up. Right? Yeah. Anything else?
Sort of one of the ultimate complex systems, right?
A complex system, you can turn a bunch of hybrid systems into a nice linear equation. Yeah, exactly.
Well, I certainly didn't mean my question to sort of damper. I hope it didn't. In any case, if you'd like to speak further to Johanna, I imagine she'd be glad to
absolutely.
hang around for a little